Today, we're going to talk about electrons and atoms, and specifically where they reside around the nucleus. Why do we care about where electrons reside? Well, in this class, when we talk about electrons, we're talking about the chemistry of an atom. How does that element react in the presence of other elements, in the presence of other compounds? And that reaction has a lot to do with those electrons and where they are located. Is there room for another element to come in and interact with the electrons from the original element? If there isn't any room, then that reaction cannot happen. So we need to know where these electrons reside. And these electrons reside in these things called orbitals. What you're seeing here on this screen is some orbitals. There are a probability of finding electrons in a certain space. So we're going to do that in a minute. We're going to start talking about electron configuration. So what is electron configuration? Well, electron configuration is the arrangement of electrons in an atom. Where are those electrons relative to the nucleus? Where are they located? Specifically, how those electrons are distributed among the various atomic orbitals in an atom. What is its address? It's electron address. Just like you have an address for your house, electrons have an address of space that they're required to be in. Okay? So where are these certain electrons located? So we're going to take a little walk down history lane and talk a little bit about that atomic theory that we talked about in previous lessons. But we're just going to focus on the two main guys. We have Bohr. Back in 1913, he said, you know what? There's been all these models of the atom, and we know that there's a nucleus, and we know in that nucleus we have protons and neutrons, and we know we have electrons. I think that those electrons are distributed around that nucleus. Not only that, I think that they are in a orbit around the nucleus. Kind of like a planet orbits the sun, he thought electrons orbited the nucleus. Okay, and he said that these orbits have a fixed energy. If you are in the first orbit, your energy is X. If you're in the second orbit, your energy is Y. They are fixed orbits and they do not change. The electrons do not exist between different energy levels or between different orbits. So this was in 1913. So this is what his model looks like laying on its side. In the middle, you have a nucleus. You can tell it's the nucleus because it's got a positive charge. And then in concentric circles around the nucleus, you have these orbits. Each of these orbits have an energy level associated with it. We have an energy level of 1 through 7 for this class. We talk about 7 energy levels, and we call those energy levels N. We'll get to that in a minute. One of the main things he said is that electrons cannot exist between energy levels. Your electrons are on those orbit concentric circles, but not in between them. Kind of like when you're playing basketball. You can try to shoot a basket into the hoop. If you overshoot, it doesn't count. If you undershoot, it doesn't count. In order for the basket to count, it must be an exact shot into the basket. Same thing here with the electron's energy. They have a very specific amount of energy. And if an electron wants to go from one energy level to another, to an excited energy level, let's say, they must have the exact right amount of energy. And we call that a quantum or a quanta. So quantum of energy is the amount of energy required to move one electron from the present energy level to the next higher one. So this is Bohr, 1913. Okay, so he said again, we have energy levels. Your electrons reside in energy levels. Okay, the closer your electron is to the nucleus, the lower that energy level. The further away it is from the nucleus, the higher the energy level. Electrons want to be as low energy as possible. They're lazy. They don't want to expend any extra energy. So they're always going to try to be as close to the nucleus as possible, assuming that there is space for them. Okay, the closer you are to the nucleus, the lower your energy. The further away you are from the nucleus, the higher your energy. So you can kind of think of these energy levels as an apartment building. So if you're in New York City and you have a walk-up apartment, a 7-bedroom walk-up apartment, you're going to prefer to have your apartment be on the first floor because it's a lot less work than climbing 7 flights of stairs. Electrons are the same way. They don't want to climb stairs if they don't have to. But if the apartments are full on the first floor, then you have to go to the second floor. You have to go to the third floor. Okay? So the higher, if you have more energy, you can go up higher. You don't want to, but you can. Okay, 1913, Bohr. In 1926, here comes the quantum mechanical model. So Bohr ruled the roost for 13 years only. Then the quantum mechanical model came. Okay, and this was three main people. We have Louis de Broglie, and he said, looking at these electrons, sometimes the electrons behave like a wave. They have properties of a wave. So you can describe them in terms of a wave function. It looks like a wave, it behaves like a wave. But sometimes it also acts like a particle, like a point. It only exists at this one spot as opposed to a continuum, which a wave has. So Louis de Broglie said there is this duality. An electron has this duality. It's like a split personality. Sometimes it acts like a particle. Sometimes it acts like a wave. And we need to take that into account when we're talking about those electrons because those electrons are important because they do all the chemistry. Heisenberg comes along and he has something called the uncertainty principle. And he said, hey, take into consideration this wave and this particle duality. We can never know exactly where an electron is because as soon as we know its position, its momentum changes. As soon as we know the momentum, its position has changed. So we will never know exactly where an electron is. Exactly where. So that is called the uncertainty principle. Where is that electron exactly? Along comes Aaron Schrodinger, and he's a pretty good mathematician. He says, you know what? I think I can describe that duality using math. And he says, so we may not be able to pinpoint that electron, but we can give it a space, a probability that we can find it in a certain area. We can find these electrons in a certain area. We can't pinpoint the location, but it'll be in a certain area. And we can define each of these electrons with something called your quantum numbers. And there are 4 of them. There are 4 quantum numbers that describes every electron. So if your element has 2 electrons, you're going to have 8 quantum numbers, 4 for the first and 4 for the second. Okay. So again, he described an equation. He called it a wave function that describes the behavior of the energies of the subatomic particles, and he brought together that particle and that wave behavior. Okay. And that led to quantum mechanics. We can't pinpoint the location of an electron in an atom, but we can define an overall region where those electrons can be at a particular time. It is a probability of finding an electron in an area, a 3-dimensional space. He called that an orbital. Okay. Again, the actual location can't be found, but we can find, there's a high probability that we will be able to find those electrons in a certain space. And it shows the probability map, this orbital has a specific shape, and the electrons are found within that shape. So let's look at the simplest of your orbital shapes. There's a orbital that is spherical in shape. Using Schrodinger's equations, his wave function, he said that there is a 90% probability of finding the electrons within that sphere. 10% probability it's going to be somewhere else. But the 90% of probability it's going to be in the space. It's kind of like if your parent comes to pick you up at school and they come to second period and you tell your parent, I'm in my chemistry class room N207 during second period. They tell the front desk comes to find you during second period into your chemistry class, and they walk in there. Pretty good chance you're in that class because that's where you're supposed to be. But maybe there's a 10% chance you're not in that class. Why? Because you went to the restroom. So you're not in the class, you're somewhere else. 10% chance you're not in the space you're supposed to be, in the classroom you're supposed to be. 10% you're outside, 90% you're inside it. And that's what this quantum mechanical model says. You've got a probability of finding an electron in a space. So in a class, so in Ridgepoint, there are many different sizes of classrooms. Some are bigger. The science rooms are bigger because we have lab space. Some are smaller because they don't need that lab space, like a math or a history class. Those are smaller. All the classrooms are different sizes. They have different shapes. The amount of students, spaces, is different. Okay, that is an orbital. We have different shapes of orbitals depending on the situation we're in, what energy level we're in. Okay, so those 4 quantum numbers that Bohr and Schrödinger came up with are the following. The first one is something called your principal energy level. That is the energy level at which your electron resides. We call that your principal quantum number, principal energy level. Next thing is your sublevel. Your sublevel. And that's like your orbital type. We have 4 types of orbitals we talk about in this class. There are more than these, but these are the ones we talk about in this class because these are the ground state orbitals. Okay? We have what's called s orbitals, p orbitals, d orbitals, and f orbitals. And we'll come back to this in a minute. Within those orbitals, we have locations. Those orbitals can be oriented in different ways. That's your ML. That is your third quantum number. So if you have 3 p orbitals and they're oriented on each axis, you have a px, a py, and a pz. And the last quantum number is your spin. That means which way is the electron facing? Electrons don't like looking at each other. So we'd like to say they face opposite directions or they have opposite spins. We usually say spin up or spin down. Okay, let's build an analogy so you kind of understand what these things are getting at. Okay, if you think of that seven floor walk-up apartment building, N, your principal energy level, is the floor you are on. So if N equals 1, you're on the first floor. You're the lowest energy you can be. N equals 2, you are on the second floor. N equals 3, you are on the third floor. N equals 4, you are on the fourth floor, and so on and so forth. Okay, your sublevels are the sizes of the apartment. So if you have an S apartment, it's a 1-bedroom apartment. If you have a P if you have a P apartment, it is a 3-bedroom. If you have a D apartment, it is a 5-bedroom. If you have an F apartment, it is a 7-bedroom. Okay, third quantum number, your orbitals. So let's say we're in a P apartment. It's a 3-bedroom apartment. What bedroom is the electron in? Out of those 3 P bedrooms, which one is it in? Is it in PX? Is it in PY? Is it in PZ? Okay, bedroom 1, bedroom 2, or bedroom 3. Where is that electron? Which bedroom? So we're pinpointing the location. And the last thing is, what does it spin? Is this electron standing up or is it laying down? How is it oriented? So you can describe what apartment you're in, what floor you're on, what apartment, what bedroom, are you standing or you're lying down? That's what we're doing with our electrons. What energy level, what orbital, what orbital space we're in, and how are electrons found. Lines, spin up or spin down. Okay, let's start with each of these one at a time. Principal quantum number, your energy level. Your principal quantum number is also called your energy level. It is also called your energy shell. Those are synonymous. Principal quantum number, energy level, energy shell. It's denoted with an N. In this class, we worry about seven energy levels. 7. N equals 1 through N equals 7. Okay, those energy levels are discrete. In other words, to go from N equals 1 to N equals 2, it's a very specific amount of energy, and it tells you exactly where electrons are found. Okay, the further you are from the nucleus, the more energy you have. The closer you are to the nucleus, the less energy you have. That is your principal quantum number. Okay. And this principal quantum number, the floor you're on, has these sublevels, S, P, D, or F. Within those sublevels, we have bedrooms, Px, Py, Pz, or all your d orbitals, and each of those can hold 2 electrons. You can sleep 2 people per bedroom. Okay, so now let's go to our sublevel. So energy level, subshell, or energy level, energy shell, principal quantum number are all the same things. Okay. Next we have our sublevel or our subshell. So we started with a level, energy level. Now we're at a sublevel. We started with an energy shell. Now we are at a subshell. Okay. These are the types of bedrooms that you have. I mean, the types of apartments that you have, 1, 3, 5, or 7. We can determine how many apartments we have by the energy level that you're in. So if you're in the first energy level, you have 1 apartment, 1 orbital. If you are in the second energy level, you have 2 orbitals or 2 apartments. If you are in the third energy level, you have 3 orbitals or 3 apartments. If you are in the fourth energy level, you have 4 orbitals or 4 apartments. In the 5th, 6th, and 7th energy level for this class, we talk about 4 orbitals, the same ones. Okay, so let's talk about those orbitals. On the first floor, if you look at the upside down triangle, on the first floor, you have 1 type of orbital, and that is called an s orbital. That's all you have. You only have an s orbital. On the second floor, you have 2 types of orbitals, 2 types of apartments, a 1-bedroom and a 2-bedroom. I mean, a 1-bedroom and a 3-bedroom. Those are called s orbitals, and we have p orbitals. So we have an s orbital on every floor, on every energy level. Our p orbitals don't start until we're in the second energy level. Okay, we go to the third energy level. We have 3 types of orbitals, s, p, d. We'll go back and talk about these in a minute. On the fourth energy level, we have our 4 types of orbitals, s, p, d, f. Each of these orbital types represents the shape of a sublevel, okay? So if you have an s orbital, it's got a very specific shape. It does not matter whether if it's in the first, second, third, or fourth energy level, its shape is the same. The size might change, but its shape is the same. P orbitals have a different shape, a different probability space. D orbitals have a different one, and F orbitals have different ones. Okay, so we talked about principal quantum number. Those are your energy levels. We talked about our orbital, our sublevels, orbitals, S, P, D, and F. Now let's talk about what an orbital is. Okay, this is our third one. Again, an orbital is the space and where there's a high probability that's occupied by a pair of electrons. Okay, these are our different orbital shapes. The top one in red is an s orbital. We're going to go through each of these individually, but the top one is an s orbital. It is spherical in shape. We have s orbitals at every energy level. The next row is your p orbitals. We have 3 of them. They're oriented on each axis, px, py, and pz. The next type of orbital we have is a d orbital, and there's 5 of them. And the last type of orbital we have, which is the green ones, is an f orbital, and we have 7 of them. Every orbital can hold 2 electrons. So we can hold 2 electrons in the s orbital. We can hold 2 electrons in each of these p orbitals for a total of 6. 2 plus 2 plus 2 is 6. We can hold 2 electrons in each of these orbitals for a total of 10. 2 plus 2 plus 2 plus 2 plus 2 is 10. And we can hold 2 electrons in each of these orbitals for a total of 14, because there's 7 of them. Okay, so we're going to talk about each of these orbital shapes one at a time. So we're going to start with the S, the round one, the simplest one. The s orbital says that if you were to find an electron in an s orbital, it's going to be traveling in a spherical shape. That's the space that's going to be the highest probability that you will find those electrons. And it will hold 2 electrons. It is a sphere. There's a high probability that you will find electrons in this spherical shape somewhere. Okay. Your sublevels, your s orbitals, you have different. You have s. I said it on the upside down triangle. I talked about how you have s orbitals at every energy level, and that is true. You have s orbitals in the first energy level. That's what this one means, 1s. You have orbitals in the second energy level. That's what this 2 means, 2s. You have orbitals in the third energy level. That's what this 3 means, 3s. You have 3 types. You have 3 sizes. Your 1s orbital is smaller than your 2s orbital, which is smaller than your 3s orbital. But they're all the same shape. They just have a different size. The higher your energy level, the larger your orbital. That's true for all orbital types. Your p orbitals on the second energy level are going to be smaller than your p orbitals on the third energy level. The smaller, the lower the energy level, the smaller the orbital. The larger the energy level, the larger the orbital. Okay, so now let's talk about p orbitals. P orbitals, or the p sublevel, are shaped like a dumbbell, or a figure 8, or a peanut, or an infinity shape, whatever you want to call it. There are 3 of them for each energy level that has p orbitals. So starting with n equals 2, second energy level, we have p orbitals. And when you have 1 p orbital, you have 3, and they are oriented like this on the 3, on the all 3 axes. On the x, this is the z, on the x, and on the y axis. Okay. Each one of these orbitals can hold 2 electrons for a maximum of 6 electrons. Each one of these orbitals can hold 2 electrons for a maximum of 6 electrons. So you go to a higher energy level, they get larger. Okay, now let's talk about what they look like to put them together. Your s orbital is round, spherical. These are your p orbitals. So if you were to put electrons in these orbitals, the first electron you would put would be in the first energy level, the 1s, which is this guy right here, the little one, the little circle. Then you'd go to the second energy level, and then you would put some more electrons in the bigger circle, 2, up to 2 electrons. Once that's full, then you can start putting electrons in the other orbitals, in the p orbitals. You can put 2 in each for a total of 6 in the blue. So in this picture, you can have a total of 10 electrons. 2 in the little s, the first s, 2 in the second s, that's a total of 4, and then 6, 2 in each of these in the p's for a total of 10. Okay, let's look at the d orbitals. So d orbitals are a little more complicated. They look like, there's 4 of them look like 4 balloons tied together. And then you've got one that looks like a dumbbell with a donut around it. Okay? Wherever you have d orbitals, if you have 1 d orbital, you're going to have 5 d orbitals available to you. Probability of finding electrons, you have 5 of them, 5 of these orbital spaces. Okay? You can put 2 electrons in each. 2 in here, 2 in here, 2 in here, 2 in here, and 2 here, for a total of 10 electrons. These are your f orbitals. Their shape is a little more complicated. You don't need to be able to draw them. You just need to be able to recognize them. But there are 7 of them. If you have f orbitals available, then you have 7 available at that energy level. Because you can put 2 electrons per orbital, 2 people per bedroom, 2 electrons per orbital, and you have 7 of them, you can hold a total of 14 electrons in your f orbitals at the energy levels that have f orbitals. That starts at the 4th energy level. You don't have f orbitals until you're in the 4th energy level. Okay. So now let's look at the energy for these orbitals. If you are at an energy level that has all 4 orbital types, so let's talk about the 4th energy level. It's the first energy level that has all 4 types. Your s orbitals are going to be the lowest in energy. Your f orbitals are going to be the highest in energy. So remember, let's make that analogy for your apartments again. We said your s orbitals are like a 1-bedroom. Your p orbitals are like a 3-bedroom, because there's 3 of them, 3 p orbitals. Your d orbitals, there are 5 of them. It's like a 5-bedroom. Your f orbitals are there's 7 of them, so it's like a 7-bedroom. What's less expensive? A 1-bedroom like an S or a 7-bedroom like an F? A 1-bedroom is less expensive. It is cost less. A S orbital has lower energy, costs less energy than a 7-bedroom. Your energy increases as you increase the sublevel. Okay, so let's look at our periodic table. I've got the periodic table colored here to show you how the periodic table is arranged. First of all, if you look at here, you've got this blue block. If you look on your periodic table and you count across, it is 2 across here. That's where your S orbitals live. That also includes your helium and your hydrogen. Okay. If you look over here, this section here on your periodic table, if you count across, there are 6 of them. Who can hold 6 electrons? P's. This is where your P's live. If you look here in this kind of flat part of your periodic table and you count across, there is 10. 10. Who can hold 10 electrons? That would be your d orbitals. If you look at the very bottom of your periodic table, you see this little like two rows down here. If you count across, there are 14. Who can hold 14 electrons? Your F orbitals. It is a good idea to label your periodic table with this. So outline the S portion and write a big S in the middle of it. Outline the D portion, write a big D in the middle of it. Outline the P portion, write a big P in the middle of it. Outline the F portion and write a big F in the middle of it. Remember your helium, you can kind of imagine being over here. So what I have on my periodic table, so I got my hydrogen here, and then I just added a square, and I just put helium right there, right next to it. So it reminds me that it's got S orbitals, and we'll talk about why that only has S orbitals in a bit. Okay, so just kind of to review, your sublevel S, orbital type S, you have 1 of them, you can put 2 electrons. Your P's, you have 3 of them, you can put 6 electrons in it. Your D's, you have 5 of them, you can put 10 electrons in it. And your F's, you have 7 of them. You can put 14 electrons in it. So let me show you some ways of writing this out. This is a shorthand way of writing out some of the stuff we just talked about. If you see, because we only have 1 S orbital, if you see one line by itself, that indicates an S orbital. Okay, and you can put 2 electrons in there. If you see 3 lines next to each other, like this, that indicates a p orbital because you have 3 of them. You can put 2 electrons in each one. If you see 5 lines next to each other like this, that indicates a d orbital because there are 5 of them. And you can put 2 electrons in each for a maximum of 10 electrons. If you see 7 lines next to each other, like this, that indicates an f orbital because there are 7 of them, and you can put 14 electrons total, 2 in each. Okay. Each line represents an orbital. Okay. You may sometimes see, instead of lines, you may sometimes see squares. If you see 1 square by itself, it's an S. If you see 3 squares right next to each other, those are P's. 5 squares next to each other, those are D's. 7 squares next to each other, those are F's. Okay. Our last quantum number is our spin, and that's telling you basically how many electrons can we put in each orbital. We've already talked about that. We can put 2 electrons per orbital, 2 people per bedroom. Okay, and they have what we call opposite spin. They don't like to have to share their orbital space, but if they are, they're not going to acknowledge each other. So if you're in an S orbital, here it's shown as a square, you can put 2 electrons in there, and you will write 1 with a spin up. This is an electron. That arrow we consider as an electron, and see how it's facing up because it's got an arrow up, and you'll have 1 that is a spin down. 1 up, 1 down. Now we're at the P level, sublevel. We have 1, 2, 3. We have 3 of them. Each of them gets 2 electrons, one up, one down, one up, one down, one up, one down. The D, we have 5 of them. They each get 2 electrons, one up, one down, one up, one down, one up, one down, one up, one down, one up, one down. F orbitals, we have 7 of them. They each get 2 electrons, each spin up, spin down. Okay, so now we've learned about how to describe these electrons by these 4 quantum numbers. Now let's use them. So again, to remind you, electron configuration is the way electrons are arranged around the nucleus of an atom. And it's governed by 3 rules. And we're going to talk about each of these rules one at a time. But first of all, we have Aufbau principle. And we're going to go a little bit more in depth for all of them. Aufbau principle says electrons are lazy. They want to go to the lowest energy level first. Pauli exclusion principle says no more than 2 electrons and they better face opposite directions. Hund's rule says I don't want to share my orbital space with you. I won't share until I have to. When I have to, I will, but not until then. Just like roommates aren't going to share a room until there are no bedrooms left, and they have to. Okay, so let's talk about Aufbau. This is the one I call the lazy tenant rule because it's like someone who's renting an apartment. If they have a 7-bedroom walk-up apartment, they're not going to want to rent the 7th floor because they have to walk up those stairs every single time. They're going to want to rent the lowest floor apartment. Electrons are the same. They're going to go to the lowest energy level orbital that is available to them. So if there is space in the first energy level where n equals 1, that's where the electron is going to go. Until that orbital is full, they're not going to go anywhere else. What does that look like? This is what's called an orbital diagram, and it shows you your different orbital types arranged by energy. If you look here at the P, see how it has 3 lines? Those are 3 orbitals. See how the S's only have 1 line? See how the D's have 5 lines? The F's have 7? That's what I meant by the previous slides. Okay, so here, if you have one electron, even though all these spaces are available to it, the electrons are going to be like, ooh, I got room down here. I don't have to do much work. I'm going to go into the 1s orbital. And then a second electron comes along and says, where can I go? Where can I go? There's all this space here. Oh, wait, I can go here. I can go into this first floor as well. Now I've put 2 electrons there. There's no more room. So now the third electron comes and he'll have to go into the second energy level until that fills up. Then the third one comes. Then once that fills up at electron number 5, we'll have to start going to another energy level. So the Aufbau principle says go to the lowest energy first. It's a lazy tenant rule. Okay. How do we remember? So I've got here this 1s, this 2s, this 2p, 3s, 3p, 4s. How do you remember what order these fill in? There's a couple ways, so I'll show you a couple ways. First of all, you can write down your orbital types by energy level. So if you remember that upside down triangle I drew earlier, I said in the first energy level, we just have S's. So that's a 1s. Ignore the green arrows right now. At the second energy level, we have S's and P's. So we're 2 for second energy level, S and 2P. The third energy level, we have 3 S's, we have 3 P's, and now we also have D's. At the fourth energy level, we have S's, P's, D's, and F's. And then 5, 6, and 7 for this class are the same because we're not talking about excited orbitals, excited energy levels. Okay, so now let's look at the arrows. Go to the bottom left right-hand corner. Draw an arrow going up. What's the first thing you see? 1s. That's the first thing you're going to fill. Next, go up from here. 2s is the next thing. Now it's 2p, 3s. Next thing to fill up is a 3p, then a 4s, then a 3d, a 4p, a 5s, and so on and so forth. Okay, they are written here. So you can put this on your periodic table to help you if you'd like. The other thing you could do is just write the filling order on your periodic table, like in a row on the bottom. Say 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. This is how it fills up. You can do that. Or you can use your periodic table to guide you. Okay? This is showing you how it fills. Okay, so we're going to use our periodic table to guide us. Remember, we labeled it. Remember, we said right here. I don't think I said it in this video, so I'm going to say it now. If you look at your periodic table, on the left-hand side, you see some numbers. Those are your energy levels. That is your N. So the first row is N equals 1. The second row is N equals 2. The third row is N equals 3. The fourth row is N equals 4, and so on and so forth. That is your energy level. So make sure you put that in label your periodic table. We already labeled this section here. These are S's. And that one there too. So again, we can move this guy and kind of imagine it being right here. Okay. These guys are P's. Now let's label these rows. 2. So on the top left-hand corner, I would write a 2, a 3, a 4, a 5, and a 6. That's the same as this energy level. See? 6, 6, 5, 5, 4, 4. But it's nice to have it there so you can keep track of things. Okay, the middle section is a D. Okay, but this is where things get a little different, and this is why you should label it. So even though we're in the fourth row, this guy is considered a 3. It's a 3D. This guy, even though we're in the fifth row, this guy is considered a 4D. 5D, 6D. So I would put in the top left-hand corner of each of these boxes, I would put 3D here, 4D, 5D, 6D. Okay, down here we have Fs. These Fs belong right here. This is where they belong, if you look at the numbers. But these are considered a 4 and a 5. So I'd write a 4F in the top left-hand corner and a 5F in the top left-hand corner for the second. So make sure you've entered that into your periodic table. Okay, so what does that look like? Okay. So if you're going to be filling, first thing you see, you go 1, S. 2, we're still in the S's here. Now 2P. Because we're going across. So we're in the 2P's. What's next? 3S. Because we're in the S's. Keep going across, keep going across. 3P. 3P, because we're in the P section. Next row, 4S. So now we hit this section right here. Remember I told you to write something in that top hand corner? That's a 3. So now we're, instead of, it's a 4S, and it's a 3D. 3D, that whole section's a D. You go all the way across. Now you're at a 4 again, P. 5S, 4D. 5P, 6S. Now look, here, we're going to drop down to here. Now we're at a 4F. Now from here, we come back up here. Look at the numbers. We're looking at the atomic numbers. It goes from 58 all the way to 71 and then back up to here. 4F. Now we're at a 5D. 6P. 7S. Now we're going to drop again. 5F. 6D. And then if we were to continue here, it'd be a 7P, but we don't have those on this periodic table. Okay, so we can use the periodic table to come up with the same thing. You can write this whole thing on the bottom of your periodic table if you don't want to use this chart, or you don't want to use the thing with the arrows. Okay, the next rule is the Pauli exclusion principle. So we had the Aufbau principle, principle, which said go to the lowest energy possible. That's the lazy tenant rule. The next rule is the Pauli exclusion principle, and that says each orbital can only hold 2 electrons, and they have to be opposite spins to each other. They have to face opposite directions. So what does that look like? Each orbital, a line being an orbital, can hold 2 electrons, and they have to face opposite direction. If it holds 3 electrons, that's bad. It can only hold 2, and they have to be facing opposite. Okay. The last rule is Hund's rule. That's what I call the empty bus rule. If orbitals have equal energy, One electron will go in each orbital before doubling up. So if you have 3p orbitals, they're all the same size, they're all the same energy. Electrons are not going to double up until they have to. Just like if you have a 3-bedroom apartment. If there are 3 roommates, you'll have one roommate per bedroom. But if you have 4 roommates, then you're going to start doubling up then. But you won't double up before then. And that's what Hund's rule says. We're not going to double up until we have to. If we have 1 electron, you go by himself. 2 electrons, this guy is not going to double up with him. He's going to take his own room, his own orbital space. Third electron is going to take its own orbital space. Now here comes the 4th electron. Oh, now he has to double up because there's no other option. Don't double up until you have to. This one we also call the bus rule, kind of like when you're on a bus. You get on the bus, first thing you do is you put your bag in the seat next to you so nobody will sit next to you. Then once the bus starts filling up more, then you're like, okay, fine. And you take your backpack off so somebody can sit with you. But you try to keep that seat to yourself. The electrons try to keep that orbital space for themselves. Okay, so those are your rules. So let's put those in action. So let's look at, just to review real fast. Aufbau principle is the lazy tenant rule. You're going to fill up the lowest energy first. Pauli exclusion principle says no more than 2 electrons, opposite spins. Hund's rule says don't pair up until you have to. So let's look at these things that have little x's next to it. Hund's rule is good here because you have these 3p orbitals. They're all equal energy. You have 1 electron in each. But if you look at the one below it, you have these 3p orbitals. And look, this guy started pairing up. It didn't need to. Why would it pair up? It should have been over here. So that guy is violating Hund's rule. Okay, so let's put that in action. Here's hydrogen. If you look at your periodic table, hydrogen has 1 electron. So that 1 electron has all these orbital spaces it can go into. Where is it going to go? Because of Aufbau, it's going to go to the first energy level. There's its 1 electron. Now it's good. It had all these spaces available to it, but it's going to go to the easiest one for it, first energy level. Now let's look at helium. Helium has 2 electrons. Look at your periodic table. It has 2 electrons. So it's going to, because of Aufbau, it's going to go into the first energy. The 2 electrons will go into the first energy level. And if they have to share an orbital, they're going to be opposite spins. So that's what happens here. You have 1 electron here. The second electron comes along and says, I have all this space available, but this is lower energy. I still prefer to be down here. So he will pair up. Next comes lithium. Lithium has a 3rd electron, has 3 electrons. So if it was going to fill up, it would go there. The 2 bottom ones are filled. Now it can go to the second energy level. Those are your 3 total electrons. Now let's look at beryllium. It's going to go 1, 2. Beryllium has 4 total electrons. Now it can go up to the second energy level. 3, 4. Opposite spins because of Pauli exclusion. No more than 2 because of Pauli exclusion. Okay, so now we're going to go to boron. Boron has 5 electrons. So it's going to put 2 in the 1s, 2 in the 2s, and then 1 in the 2p. Also got carbon. Carbon has 6 electrons. How is it going to fill up first? It's going to go to the 1s. I put 1 electron there. Here comes the other one. It's going to be opposite spins, but in the same box. That's 2 electrons. Here's number 3. Here's number 4. Here's number 5. Now, because of Hund's rule, it's not going to pair up. 6. Next, we have nitrogen. It has 7 electrons. This is what it looks like. Number 1, 2, 3, 4, 5, 6, and 7. Okay, that's all we got for you today. Please check back for electron configuration in the next video.